This conversation is powered by Google Illuminate. Check out illuminate.google.com for more. Welcome to the Stression. Today we're delving into a comprehensive survey paper on time series forecasting, focusing on the architectural diversity and open challenges in the field. The paper highlights a significant shift away from the dominance of transformer models. What are your initial thoughts on this evolving landscape?
The shift is fascinating. For a while, transformers seemed to be the universal solution for time series forecasting, largely due to their ability to handle long-term dependencies. However, the survey reveals that simpler architectures, even basic linear layers, can sometimes outperform transformers, particularly in long-term forecasting tasks. This underscores the importance of considering the specific characteristics of the data and the limitations of any single architectural approach. The one-size-fits-all approach is clearly not optimal.
The paper mentioned the limitations of existing surveys. What are the key shortcomings it addresses, and how does it offer a different perspective?
Existing surveys often focus on specific architectures in detail, neglecting a broader comparative analysis. This paper aims for a more holistic view, comparing the evolution and performance of various architectures: MLPs, CNNs, RNNs, GNNs, transformers, diffusion models, foundation models, and even the newly emerging Mamba models across different criteria. It also delves deeper into open challenges like channel dependency, distribution shift, causality, and feature extraction, providing a more comprehensive understanding of the current state of the art.
Let's discuss the renaissance of architectural modeling and time series forecasting. What factors contributed to this shift away from the transformer-centric approach?
The limitations of transformers in long-term forecasting played a crucial role. Their quadratic time and memory complexity becomes a significant bottleneck when dealing with extensive historical data. The paper highlights studies showing that simpler models, particularly linear models, can better preserve temporal order information and extract relevant features like trends and seasonality, sometimes outperforming transformers. This spurred renewed interest in exploring and refining traditional deep learning architectures.
The survey emphasizes the importance of addressing open challenges. Can you elaborate on the significance of channel dependency in multivariate time series forecasting?
In multivariate time series, understanding the relationships between different channels variables is critical. Intuitively, we'd expect models that explicitly model these interchannel dependencies, CD, to perform better. Surprisingly, the paper shows that channel-independent CI strategies, which treat each channel separately, sometimes outperform CD strategies. This highlights a complex interplay between model architecture, data characteristics, and the presence of distribution shifts.
The paper discusses distribution shift as a major challenge. How do the proposed methods attempt to alleviate this issue?
Distribution shift refers to discrepancies in the statistical properties of the data between training and testing sets. The survey focuses on normalization-denormalization techniques. These methods normalize the input data to stabilize the distribution before feeding it to the model, and then denormalize the output to restore the original scale. Different approaches vary in how they estimate and apply these normalization and denormalization parameters, aiming to account for the dynamic changes in data distribution.
The emergence of Mamba models is another significant development. How do these models differ from transformers and other architectures, and what are their key advantages?
Mamba models are based on state space models, SSMs, offering a different approach to sequential modeling. Unlike transformers, they don't rely on attention mechanisms, resulting in linear time complexity. They also incorporate a selective SSM that dynamically adapts to the input data, allowing for efficient processing of long sequences. The key advantages are their computational efficiency, scalability, and ability to handle long-term dependencies without the quadratic complexity of transformers.
The survey also touches upon foundation models for time series forecasting. What are the key challenges and approaches in this area?
Building foundation models for time series faces challenges related to data diversity and availability. Time series data from different domains, weaving finance, weather, healthcare, have unique characteristics, making it difficult to create a general-purpose pre-training corpus. Approaches include leveraging the sequence modeling capabilities of large language models, LLMs, by fine-tuning them on time series data or creating large-scale pre-training corpora from diverse sources.
The paper discusses the use of diffusion models in time series forecasting. What are the advantages of this approach, and how do they address some of the limitations of other methods?
Diffusion models are generative models that gradually add and remove noise from the data. In time series forecasting, they can generate probabilistic forecasts capturing uncertainty. The survey highlights the importance of effective conditional embedding, using past data as a condition, and the integration of time series feature extraction techniques like decomposition and frequency domain analysis to improve their performance.
The survey covers various feature extraction techniques. Can you summarize the key methods and their impact on model performance?
Key feature extraction techniques include decomposition, separating trend, seasonality, etc., downsampling, reducing the number of data points, multi-scale analysis, considering different time scales, and domain transformation, e.g. Fourier transform to the frequency domain. These methods help simplify complex data, reduce noise, and highlight important patterns, leading to improved model accuracy and efficiency.
The paper concludes by mentioning some limitations and future research directions. What are some of the key areas that require further investigation?
Future research should focus on developing more robust methods for handling distribution shifts and improving the interpretability of complex models. Further exploration of causal relationships in time series data is also crucial for building more accurate and insightful forecasting models. Finally, creating larger, more diverse, and publicly available time series datasets is essential for advancing the field of foundation models. The domain-specific nature of much time series data also necessitates further interdisciplinary collaboration.
The paper emphasizes the importance of considering both the characteristics of the data and the strengths and weaknesses of different architectures. How can researchers best navigate this complex landscape?
Researchers need a holistic understanding of time series data and the various deep learning architectures. Careful consideration of the specific characteristics of the data length, dimensionality, stationarity, presence of noise, and intervariable relationships is crucial for selecting the most appropriate model. Benchmarking different architectures on diverse datasets is essential for evaluating their performance and identifying their limitations. Furthermore, a combination of techniques, such as feature extraction and distribution shift alleviation, can significantly improve the robustness and accuracy of forecasting models.
The survey highlights a move towards hybrid models that combine the strengths of multiple architectures. What are the advantages of this approach?
Hybrid models offer a powerful way to leverage the unique strengths of different architectures. For example, combining CNNs for local pattern extraction with RNNs for temporal dependency modeling or integrating transformers with diffusion models for probabilistic forecasting can lead to improved performance. This approach allows for a more nuanced and tailored approach to time series forecasting, addressing the limitations of any single architecture.
In summary, this survey provides a valuable overview of the current state of time series forecasting, highlighting the architectural diversity and the ongoing challenges. Thank you for this insightful discussion.
You're welcome. The field is rapidly evolving, and this discussion has only scratched the surface of the many exciting developments and open questions. Further research is needed to fully unlock the potential of time series forecasting.
Indeed. The interplay between architectural choices, data characteristics, and the handling of open challenges is a rich area for future research. Thank you again for your expertise.